Alright, 6.4 exponential growth and decay. It's not an easy section because there's all sorts of different exponential equations that you can use. You've got the money one where you've got the amount is P e to the RT. That's exponentially growing. That's when it's compounded continuously. You've got the P times 1 plus R over N to the NT, where it's compounded N times in a year, where R is the decimal rate, or the percentage rate in decimal form, T is the years, P is the initial principal, and the A is the amount you end up with. So you've also got like velocity equals v sub 0 e to the negative kt. It's just another version of physics application, but really it's the same thing right there. You also have, the way I've taught it before, is art or earth, r to the t plus h. So h is the horizontal asymptote. If the horizontal asymptote is 0, then it's just art. If it's like becoming room temperature or something like that, let's say room temperature is 70 degrees, then h would be 70 degrees. So it'd be y equals a r to the t plus 70. And let's say I just pour myself a cup of coffee, and initially when time is 0, our temperature, call it y here, is, I don't know, 200 degrees. So then you could say 200 equals a r to the 0 plus 70. Subtract 70, so a ends up being 130. So our equation would be y equals 130 r to the t plus 70. So in this situation, the a plus h is always going to equal your initial temperature. So if I knew that was 70, I would know right away that's 130. That's just the way it'll work out. So a plus h is our initial, and then we would need one other temperature or initial value. So let's say after 10 minutes our temperature is 120 degrees. Then you can find out what r is, and from there answer the question. So 120 equals 130 r to the 10 plus 70. What's that? 5/13. The 10th root of 5/13 is what r is. And then, so we have our entire equation, 130 times the 10th root of 5/13 t plus 70. If you want to know what the temperature is after 20 minutes, you'd put 20 in. Or if you want to know when the temperature is 100 degrees, you'd put 100 in for y and solve for t. Okay, so that's just one example of exponential. Another one, as far as that, wasn't really even calculus, that was just using algebra or pre-calc. If you have, let's say I have the populations equal to 10 e to the 0.2 t, and I wanted to find dp dt. dp dt would equal, well, the 10 floats, e to the 0.2 t is e to the 0.2 t times the derivative of the exponent, which is 0.2 or 2/10. Okay, so I could rewrite that dp dt equals 0.2 times 10 e to the 0.2 t, which we know is actually p. So dp dt is 0.2 p. So that is a differential equation because it's a derivative, and the dependent variable is actually in our derivative. So 0.2 p. If I had done p equals 50 e to the 0.2 t, then my derivative would be 0.2 times 50 e to the 0.2 t, which is still 0.2 times rp. So as long as it's in that form, this is a kind of a family of exponential equations. If I was going to draw a slope field, this would be one solution, that would be another solution, and they'd all be, there'd be infinite amount of 0.2 p derivatives on our slope field. Okay, but that's an indicator that it's exponential. If it's just a constant times p, that means it's going to be an exponential equation or differential equation. All right, so this 0.2 would be the growth rate, and the p would be the, well, it's the population or the dependent variable, kind of like our y typically would be, but here it's p. Okay, so I want to show another example. If I've got a population, and let's say our birth rate, let's say the population is going up 0.00004 p. That's our birth rate. And our death rate is, we'll say 0.00000. Well, let's have the same amount of zeros, so I'll make it 5 zeros, so I'll add another 0. Easy fix. There we go. 1 p. Okay, so our population is going, well, our birth rate, there's our death rate, so our growth rate would be birth minus our death. So our birth rate would be 0.000003 p. So that's our growth rate. And we know growth rate times are kind of like what we just did right here. Growth rate times our population is what the rate of change of our population will be. Okay, so our growth rate is right here. I'm going to say dp dt equals our growth rate times our dependent variable, which is just p. So from this information, if we know our birth rate and death rate, and we know, if we know that the population of this city, I guess, is changing exponentially, then we can say dp dt equals 0.000003 p squared. Okay, so there's our differential equation. Let's give ourselves initial values. So let's say at the current is 10,000 people, and we want to know population in 20 years. Okay, so is it going to be more or less than the 10,000? Well, we have a positive growth rate, so it will be more than 10,000 in 20 years because this is the model that we created and we are growing the population. So we have an initial value problem. We can solve that by, in this case, we're going to have to separate the variables because I have p's on this side and they belong over here. So I have dp dt times 1 over p squared. So now you can integrate with respect to t, so we end up with integral of 1 over p squared dp equals integral of we're integrating both sides with dt, which will get rid of that, so it's dt. Okay, so antiderivative, this is just p to the negative 2, so the antiderivative of p to the negative 2 would be negative 1 over p. Antiderivative of a constant is just, in this case, plus c. Alright, so I have my equation. Almost, I need to find out what c is. Well, we know that when time is 0, population is 10,000. Get tired of writing all these zeros. So c is negative 1 over 10,000. Now we have our equation. We have negative 1, it's kind of ugly, 0.00003 t minus 1 over 10,000. Okay, I haven't solved for p yet, but now we know that we're trying to figure out what the population is in 20 years. So I can put 20 not in for the population, in for t. So negative 1 over p equals 320 minus 1 over 10,000. Alright, so negative 1 over p equals that number, which is, I don't know, negative point, or point, you can't even see it, negative 0.00004 or something. So equals that number. I'm going to multiply that number times p, and p would be negative 1 divided by that number. So I'm going to do negative 1 divided by that number. Negative 1 divided by the answer. And I get 25,000. Seems like a reasonable answer. So our population would be 25,000 people in 20 years. That's quite a bit of growth in 20 years to go from 10,000 to 25,000, but that seems pretty reasonable.